Welcome back, everybody. The second week started, and this section is for visualization for biology data set. And then I'd like to introduce Dr. Michelle Borkin. She's assistant professor in the College of the Computer and Information Science. No assistant. Her specialty is for visualization of the data set. And I'm really happy we can invite you again this year. And then please enjoy her talk this morning.
Great. Thank you for the introduction. Let me just get my little timer started here. I want to make sure I don't talk your ears off too much and I leave some time for questions. Oh, timer crashed. Okay. Dan, if you can just wave at me when we're getting sort of closer to the end to make sure I have time for questions. Sure. That would be great. Okay. So let's see. And I apologize, a lot of my slides are dark, so they're washed out for the moment. I might turn all the lights off later and hope you all will not fall asleep on me. So the introduction is, yes, I'm an assistant professor here, and my area of expertise is data visualization. I'm part of the data science and human computer interaction faculty groups in the computer science department at Northeastern University. But my background is not in computer science. I am a hardcore physics and astrophysics scientist who later in the game turned into a computer scientist, and sometimes I still have to be like, what? I'm in a computer science program? But it's really important for me, for my research, and I work with scientists from across different domains, including astronomy and physics and bioinformatics and medical physics, to sort of be like, I came to this field from a different angle. So here I am in college, a little washed out, but at the Green Bank Radio Telescope in West Virginia. So my legit original expertise is being a radio astronomer and doing astrochemistry and studying the molecular composition of star-forming regions. And here I am at my senior year of college. What happened was, for my undergraduate senior thesis, I had to visualize large amounts of data. I had like 3D volumetric data, I had sort of abstract data, time series data, and that threw me into the realm of data visualization and computer graphics. I was so hooked on having so much fun doing this, I withdrew all my astrophysics PhD applications to sort of take a few years to figure out what I was going to do, and became a research assistant in doing computational physics, but with a focus on data visualization. I truly loved that so much that I went to graduate school to get PhD, and somehow over the course of my PhD, even though I started in applied physics, by the end of it, all my publications were in computer science journals, and realized, career shift might have happened without me realizing it. I did a postdoc and then joined the faculty here in 2015. So here's the timeline of me for the past 10 years or so. And I always like to amend this timeline and add another little facet to it, which is, what was I doing not at the office? And I got married at the end of my PhD, met my husband while in graduate school, and I'm the proud mom of a little baby girl. And I will note that I was right here, as I mentioned, that this was my passion for data visualization. And even though I had been doing data visualization as part of my computer science, my math, my statistics, my physics courses, I sort of didn't realize that there was a whole domain of data visualization, a whole field of visualization. So now I'm going to try and answer the question for you, what is visualization? Just to make sure we're all on the same page, and I think all of you, having signed up for this part of the May Institute, kind of know the answer to this, but I just sort of want to formalize it, and it'll help set you up for the next couple days of wonderful workshops. Okay, so what is visualization? By definition, visualization is the visual representation of data to reinforce human cognition, or more simply put, things like these. These are all different static data visualizations. You have plots and maps and different things. But I'm going to amend the sort of conventional definition of data visualization to say that visualization is the static or interactive visual representation of abstract or spatial data. So all of these are static visualizations. Interactive would be anyone who checked the weather and looked at the weather map on their phone, or the stock market, little line charts. any of the beautiful interactive news stories from the New York Times, even 538 does them, but sort of interactive visualizations and data graphics and interactive infographics are becoming quite common. And then abstract or spatial data. Abstract is anything quantitative you're going to plot in statistical plots like these. I think most of what we're going to be working with is, through this workshop is abstract data, but spatial is sort of just a, specific sidestep to say spatial data is things like maps, anything that physically maps to real world objects or real world geography. Now, visualization, where does it come from? It's a fascinating field. It's one of the reasons I love to work in it is it's highly interdisciplinary and has sort of grown out of different fields in different ways. So as an academic professor of computer science, it came out of computer graphics. So there's the SIGGRAPH, so ACM, SIGGRAPH, huge computer graphics conference for the past 40 years. And there was a splinter group. It started like as a track and then became its own special interest group, like workshop at the meeting. And then they threw themselves off on their own for doing scientific and information visualization. That came out of the computer graphics community of saying, we have a plot. Literally, how are we going to make pixels on our screen to represent this plot? And you have examples like these. These are sort of just a variety of other visualizations. The beautiful 3D scatter plot there from a physics simulation is sort of more where it grew out of the computer graphics community, but in all these other renderings. And these are sort of what we conventionally think of visualization, but I should be noting that visualization is very old. It has hundreds to arguably thousands of years of history and how we've been making them. So maps are some of the older ones. Even people argue with me for linguistics. You have Florence Nightingale, who invented the sector pie chart, and she was a huge advocate for public health and did epidemiology, and she went around trying to convince hospitals in England that they need to improve their sanitation and hygiene. And the pie chart here, these huge sectors are showing soldiers who were injured, but they should have been able to survive, but they died due to poor sanitation on the field or in the hospital. So she invented that. William Playfair invented the bar chart. There's the first bar chart ever made. And William Playfair also did line chart and area chart, all for economics and trade data. And then Charles Menard was an engineer and did this famous Napoleon's March, and he did a lot of beautiful sort of multi-panel, we call it, probably very arguably almost very early infographics where you're telling a story with multiple plots. So visualization, just to say, has this lovely old history, and this is a more contemporary look at them. And probably from the last 20 years, the other basis for contemporary visualization is statistics. So all the papers I cite when I'm writing papers and when I teach in my class, from basically the 80s through 90s, they're all published in stats journals. And that's where we're talking about representation of bars and stacked area and error and uncertainty representation. But visualization also draws from design, art, psychology, and human-computer interaction. So the HCI gets into how you interact with the visualization and click on points. There's a whole science behind that. And I'm going to give you some demos of psychology, which gets into visual perception, how you see color, how you see grouping. And Stephen Braun, who you'll hear from later today, I believe, is going to talk a little bit more about those concepts as well as art and design. Okay, but why do we need visualization? That's the what it is, but why do I have a job? And that's because there's a lot of data out there. And I think most of you are in this room because you have data. It may not be huge data, but you have data and you need to understand it and explore it and visualize it. And the stats to go with this are that I have a bunch of dark videos coming up, so don't fall asleep on me. You can see it a little better now. Every day, 2.5 million terabytes of data are created, and that 90% of the data currently in existence was created just in the past 2 years. So this is a true explosion. And the projections say that you'll have more than 40 zettabytes of data by 2020. So in case you didn't know what a zettabyte is, I didn't. I had to look it up. It's 40 with 21 zeros at the end. So there's a lot of data out there. Where is the data coming from? It's coming from everywhere. You know, so LSST is an astronomy survey, we have gene sequencing, you know, text digitization, simulations and maps, financially, it's everywhere. I think all of you are contributing beautifully to this bubble and burst of data. And these large amounts and diverse types of data pose many challenges for all of us who work in data science, but some of these challenges, I feel and argue, visualization is particularly beneficial and attuned to helping. So issues of scalability. You might have a small little data set of, say it's a network diagram of dozens of nodes, but then what happens when you have millions of nodes? How you just can't look at that much data, and you need to find ways to represent it and simplify it, and part of that is complexity reduction. Sometimes it's not, you don't plot 5 million nodes, you find ways to filter your data or aggregate it or do, you know, large nodes with little ones in it to sort of simplify it. And complexity reduction is a big thing. You can have a gigantic Excel table, but fundamentally one bar chart might be simple enough to summarize what's in there to understand. And a big part nowadays is keeping humans in the loop. All of this data is being sorted and analyzed in many ways algorithmically. It could be sophisticated statistical processes or algorithms, but it's also the advent of AI and machine learning. And there's a whole realm of visualization now being built around explainable AI and sort of keeping humans in the loop to understand what's happening with their algorithms and understand how their data is being processed, let alone a lot of my work is working with scientists who are doing data workflows and working with BLAST and all these like bio platforms, and you want to sort of have benchmarks and have visualizations to check along the way to make sure your experiment's running properly, or if you have a simulation to make sure it's not crashing. If it does, how are you going to debug it? One game I like to play with, oh, actually, before I do the game, here is an example I have of a big data visualization problem I worked on as part of my PhD dissertation. In case you did not recognize this, this is the Cassiopeia A supernova remnant. It's one of the youngest in our galaxy, about 330 years old. And a friend of mine who at the time was at MIT, Tracy Delaney, had 8 years of gorgeous data from the Hubble Space Telescope and Chandra X-ray Telescope and Spitzer, and she had all these ground-based telescopes in Arizona and Hawaii. And she had no idea how to put all of her data together to study the supernova. And this was sort of the final rendering we made for the press release for our paper, but I do lovingly call this the Hollywood version of her data. This is the cover of Vogue magazine. It looks great data. The first draft I made for her looked like this, and she gave me that wonderful aha moment, and she could instantly see that the explosion was asymmetric, and it had these embedded concentric shells from these different shock fronts, and you had these jets, and they weren't angled to how the theory predicted they would. And sort of her exploration of this data and visualization to sort of line everything up changed the way she and others understood this supernova, as well as the sort of theory of supernova explosions in general. But what Tracy didn't realize is that the software I used to do her data cleanup, the registration, the analysis, and the visualization was a tool called 3D Slicer, which was originally developed for doing surgical planning at Brigham and Women's Hospital and identifying and doing planning around brain tumors. So the theme for my talk is going to be interdisciplinary, that many of the problems and challenges you all face with your data analysis and visualization really is ubiquitous and common among other areas of science. And this is just one example, and that the tools you can build and develop for one domain are actually going to be able to help others, or your solution might be out there already. And so when I work with scientists and doctors and physicists and psychologists, I have this challenge where I have to convince them that their problem is the same as somebody else's problem, or that what they're doing is like, I know how to solve this, but it's from this other domain of, related to visualization. So I play a game with them called Which is Which. And here I have a biological data set and an astronomical data set, and I have a series of these, pairs of images, and I get them to look at them, and I have a really fun time getting doctors to diagnose what disease a patient has, and they're really looking at the Andromeda Galaxy, and they're like, oh, I didn't realize that. So we're going to take a little poll here. One of these images is biological, and the other is astronomical. So take a minute, and I'm going to have you raise your hand to vote which is which. So raise your hand if you think the one on the left is the biological image. Raise your hand if you think the one on the right is a biological image. Ooh, it's tricky. But I think the majority had it, that on the right you have an angiogram of a patient's heart, and you're looking at blood flow going through the heart with contrast dye. And this is some of the raw data from the Cassiopeia A supernova remnant I was just showing you. Okay, now we're going to try another one, and this is a little trickier and closer to what I work with on a regular basis. Now tell me which one's the biological, which one's the astronomical. Take a minute, take a peek, and then we're going to take a poll. The images look much better on my computer screen, but you get the gist of it up there. Okay, so raise your hand if you think the one on the left is the biological one. How about raise your hand if you think the one on the right is biological? So it's about 50-50. That's how I designed this. It's a lot harder, but the one on the left is a confocal microscopy image of a human cornea, and on the right is the NGC 1333 star-forming region. But what's fascinating is they do look really similar. The resolution is similar. The noise patterns are even similar between the microscope and the telescope over there. And what the doctors are looking for in the confocal microscopy image, things like Fuchs disease and calcifications, parallels incredibly well what the astronomers are looking for in the other image of young stars being born as having a similar representation of these sort of bright, dense regions. And these doctors and astronomers are both analyzing these images as well as having all sorts of other statistical plots to go with it. Now, in case you've never seen, most of you probably have, but in case you have never seen where all this raw data comes from, here's an MRI scanner, and here's some raw MRI data of a human head, and here you're looking at the patient's face, and it's sort of stepping through and slices through the head. You can see their brain in the middle, and then as the scan steps through the back, you can see the back of the head. And this is sort of like a very standard, typical DICOM MRI data set. And turns out it's essentially similar to how you process and get the data out of radio telescopes, or here we have infrared telescopes, an array of them, and it's nearly identical to how the data is being built and processed, a little different in terms of how the spectroscopy is happening in the back end, and the data comes out the same way as these lovely slices. So this is the M16 nebula. You're looking at the front of the nebula, and as we're stepping back through the nebula, you can see these bright regions where you have young stars being born to the back. Now, as I showed you earlier, sort of the medical community has done an excellent job over the years of developing visualization tools and 3D rendering and analytics packages. Not so much in the astrophysics realm. Quite behind the times. Even I've been giving this talk for, this argument for many years, and astronomy is doing better but still has some catching up to do and has very limited visualization. So when I attacked this project, I decided to help out Mark Pound, who made the other beautiful visualization working with Alyssa Goodman over at Harvard. And that nebula is showing you, M16, is this one here. It's one of my favorite Hubble telescope images. It's the Pillars of Creation, or the Eagle Nebula. And this is an optical image, but I'm going to fade it out onto the data set I was working with, which was a radio telescope data. And you can still sort of see in the background 1, 2, 3 pillars. I'm going to fade out this image so you can see the false color radio telescope image. And this is looking at the really, really cold, dark, fluffy gas that you can't see with the naked eye. And this was, again, OSIRIX, another visualization toolkit for medical. We were able to visualize this in 3D, and Mark, it was so cool. He was so excited when he saw this. And let me pause the video 1 second. here, because he had been spending years trying to convince people through basic plots and statistics that there was a supernova, there's a shock wave nearby, and it was blasting through the nebula, and it was heating the gas up and causing young stars to be born. And he had no way to like convincingly present this information. And right here you can beautifully see the shock wave from the nearby explosion, and it's actually pushing and toppling the pillars over and heating them up and causing the star formation. So I've spent the last 10 years or so working as a visualization expert with scientists and doctors from across different domains of astronomy and physics, engineering, psychology, doing visualization of computer science and systems data, and then in the medical community doing some bioinformatics visualization and work with cardiologists and radiologists, neurologists all across here. I obviously cannot cover all of this today, and you will see many more examples of beautiful biophysics and biologically based data through the rest of your next couple days. So I'll show you a little bit here, but I'm going to focus on some other examples just so you can see how the visualization is important and see some different pieces. So what do I work on in my actual research? I'm going to come back to the astronomy stuff at the very end of the talk, but other things I work on are computer-assisted diagnostics at hospitals. So I work with cardiologists and neurologists to do a lot of blood flow and artery visualization, and then gets into doing modeling of literally down to the level of how the endothelial cells are functioning on the inside of the arteries and simulating lipid deposits. I do work with doctors doing glaucoma diagnostics and doing these sort of these different abstract representations of data to help speed up patient diagnostics. And I also do some work with brain tumor diagnostics and visualization and trying to help doctors using machine learning code understand what's happening and how they're identifying tumors. Another realm that I work in is perception and cognition, and this gets into the realm of psychology, and I have a bunch of psychology collaborators here at Northeastern as well as at MIT, and we design and execute different types of experiments to understand at the lowest level how people are seeing and visually understanding visualizations and perceiving them, as well as understanding, and we have been working on memorability and comprehension to say how can we change the layout or change the text or change the color of a graph to make it easier to understand. So some of the experiments we've been doing, and this is all at massviz.mit.edu if this piques your interest and you want to read more about it, and scraped as part of my dissertation this giant almost 6,000 visualization database from news media websites, government websites, infographic blogs, as well as nature and science scientific journals to make this huge database of sort of in the wild visualizations and do all sorts of experiments on them. And most of this is on Mechanical Turk, so we crowdsource this. And here's one example of a paper we wrote about memorability. So how to make a visualization memorable if you're doing communication or education, or even you're writing a journal paper and you want people to remember the main point of what you're trying to make. And so these are the most and least memorable. I'm not saying those least memorable ones are bad visualizations. It's just how can you do more effective communication, and turns out annotation and color is really important, and did some follow-up work on that with another paper using eye tracking, and here I am in an eye tracking setup looking at visualizations and sort of tracking where I see. And now we sort of have memorability versus other things on the x-axis. So this plot was looking at comprehension. We had participants type up text blurbs about visualizations, and the top right quadrant sort of became the sweet spot to say how you make something that's memorable and people understand what's going on. And in that work, sort of the pieces are having sort of good visual form and elements, good text, and having good communication of your main message through message and data redundancy, and titles and annotations. I could give you a 2-hour keynote lecture just on this one slide. I'm not doing that today, and a lot of what I would say on that version of this talk, Stephen Braun's going to cover later. The biggest takeaway from the little red text up there is please put titles on your visualizations. That was the punchline of our big study, that titles had the strongest influence on people understanding and remembering what's in a plot. So make sure and label your axes, label your graph and put a title on it, And annotations, I know it's common sense, make a huge difference. Put an arrow pointing to the most important thing in your scatter plot. Or if you have a matrix plot, put like a stroke box around the part of your matrix plot that's the most important for someone to look at. That those subtle, very simple visual and textual annotations dramatically increase how well someone can remember and understand what's going on. So that's my 2 cents for you on all the cognition work I've done. And then the sort of other piece of this that's sort of fallen out in the last couple years is doing the eye tracking work. Turns out eye tracking data is really hard to visualize and understand. So I've been publishing a lot of papers on how to better visualize eye tracking data as a consequence. Okay, so that's sort of the lay of the land of the stuff I work on and my visualization and scientific backgrounds. And now I'm going to take the next 20 minutes or so to dive into one particular project in depth and sort of show you the power of visualization and how subtle differences in how you represent data can make a dramatic change. And this is, I'm zooming in on my cardiovascular visualization research. Let me quickly pause before I jump into this particular project to ask if there's any high-level questions at this point. I'll take questions at the end. But okay, excellent. So what you're looking at here is a sort of state-of-the-art 3D rendering of a patient's coronary arteries. So the coronary arteries, here's a medical school textbook diagram of your heart, and I shall use the physical hand demo. In case you didn't know, your heart is about the size of your hand. There's your little cocktail party factoid. And the coronary arteries wrap around the heart and supply blood to the heart. So the doctors care about these arteries because if you get blockage or rupture, you are going to have a heart attack and probably die. So the goal for this project coming in was how to best visualize blood flow data for the doctors of these arteries so they can diagnose a patient. All right, so on the left, when I joined the project, I was brought in as someone who could both work on the physics simulation as well as the visualization works or simultaneously. This was the state of the art. By the time I was done with my design study, this is the representation I came up with as my hypothesis for the best way to represent this data and help a doctor diagnose a patient looking for unusual blood flow and plaque deposits. So for the next few slides, I'm going to sort of walk you through how I got from this more conventional 3D representation to these kind of off-the-wall 2D abstract artery flattened projection visualization. And let's start by doing a little background on how you diagnose heart disease so you sort of know where the doctors were coming from. Currently, hopefully no one in this room has had to deal with this, but if you are suspicious that there's a heart issue, you have pounding heart, shortness of breath, especially going up and down stairs, then your doctor is going to do a bunch of blood work. They're going to do a stress test on you, so put you on a treadmill and you're going to jog. And if your heart function's still looking suspicious, they do an echocardiogram to do an ultrasound. If that doesn't look good, then they do an angiogram. I have a bunch of friends who are doctors, and they always get really frustrated with me at this point when I sort of talk about this research, because they're like, angiography is not a big deal. It's an outpatient procedure. It's not a big... I'm like, I don't like needles, and I don't like having invasive things done. This is icky. In angiography, they have to do an incision in your groin and snake a wire up to your heart and inject dye. And then they do a bunch of x-ray images to see how the dye is propagating through your arteries. And it doesn't show all the details you need. It's like a 4 to 6 week recovery from the incision. We don't want that. So thankfully, there are lots of medical teams out there working on non-invasive diagnostic procedures, and these are becoming more and more common. Hooray! And what you do is you just go in for a CT scan. 20 minutes, no procedure, no nothing, and you're out with minimal side effects. So this sounds a lot better to me. So you go in and you get a CT scan. Then we segment the artery. So we go through that data set like you saw for the brain with the MRI. It looks nearly identical. And there's an algorithm that can find and identify all the coronary arteries wrapping around the heart. And then these get cleaned up and extracted into sort of a patient-specific geometry. It gets passed into a blood flow simulation to figure out how the blood's going through the arteries in the heart. We then visualize this data and then present it to the doctor. So this is all work I've been doing with doctors at Brigham and Women's Hospital, but there's other doctors down at Duke University, and I think it's UCLA or UC San Diego, similar. Okay, but it's trickling up into the hospital system. So this is the whole pipeline, but today I'm just focusing on the last two steps here. And if you have questions about all these other pieces or like the physics behind it or the simulation, I can tell you at the end. But it's really, once we have the data, how we present it to the doctors to visualize and then make a clinical decision. Okay, the data, what are we working with? Here's a cross-section of a human's coronary artery. And this little bit of yellow here is the plaque. This is the initial disease. And it turns out that these areas of plaque have been, through lots of research, it's sort of established of areas of low ESS. ESS is endothelial shear stress, which in other words is the frictional force of blood. So take my word for it. I can explain the physics later. But as the blood goes through your artery, if it's low friction, that's where all the plaque deposits happen. So from a fluid dynamics point of view, we want to identify these areas of low friction. So what happens to the patient is 20 years of bacon cheeseburgers and bad eating. You get more and more of the lipids. You get bigger and bigger plaque deposit. The physics is self-reinforcing, so that low friction gets lower and lower and lower, and you get this yellow bubble here. And this is what's going to rupture and give you a heart attack. So the sort of goal for the visualizations when I did this project was make visualizations that identify that scary plaque deposit. That's the point. Now, everything I just told you in the last two slides, you can forget for the rest of the talk. Not important. Just remember that as I show you visualizations and plots, low shear stress is bad. That means it's related to disease tissue and the plaque deposits. And as a side note, the reason we have to have the blood flow simulation is you cannot directly measure this shear stress frictional force in a living patient. It's impossible to do so. So we need to rely on these calculations from the simulations to do it. Okay, so back to where we were a couple slides ago. Conventional representation, I join the project and I produce this representation on the right. So now the question for the next couple slides is, how did I come up with this alternative visual representation of the 3D data and why? So in order to do this, I did a formative qualitative study, and I did this with a bunch of semi-structured interviews with 10 doctors, all of them at Brigham and Women's Hospital, and I asked them questions about these two steps. I wanted to understand what are they looking for when they diagnose a patient, what's important, what data are they using, and sort of what tools do they currently use. And that was really important to sort of get a lay of the land, and then I did follow-up interviews with these same 10 doctors to present to them a bunch of my initial sketches and ideas before I wrote a single line of code, before I made a single plot. I made sure to do all this sort of contextual research in the hand-drawn sketching or digital sketching to make sure I was going to build the right tool and develop the right system for them. So the first thing I realized is, these 3D renderings are the conventional state-of-the-art for the doctors to use. But they all in their interviews sort of fessed up to some of the challenges of working with 3D. So does anyone want to sort of hazard a guess as to what one of the sort of disadvantages of this representation is? For a small enough group, I'm going to turn this keynote interactive. Yeah?
Some structures are hidden.
Exactly. So you're only looking at the front of the arteries. The problem is you have to look at the back of those arteries because there's all sorts of other arteries and structure and this blood flow data on the back side. So this is the huge problem of occlusion with the 3D rendering. How do the doctors get around this right now? There's sort of a couple things. If they're in a clinical patient, clinical room and they're like with patients, what they can do is they have a hand free. They can use a mouse to rotate the model. The most common thing is when this data is generated, it gets output as like a movie, like an MPEG or a QuickTime movie, of it rotating, and then they sort of scrub and drag the little slider for the movie to sort of make the model rotate. What do they do when they're actually doing a procedure? So a lot of times they want to look at this data, or actually they do the angiography data too, in real time while they're working on the stent insertion, for instance, in a patient. Well, the procedure rooms have a separate computer terminal on the side with a dedicated nurse, and they usually have a screen mounted above the procedure table, and the doctor says, move the model to the left, move it to the right, change the view, and the nurse does it over on the other side of the room. So this was my thought of, why do we need to have this interaction? This is a huge barrier for the doctors when they're doing diagnostics and making quick decisions or working on a patient. So let's make something that's two-dimensional. Let's throw out the interaction. We don't want it. So here was my first draft of a 2D representation of the 3D arteries. And my second sort of round of interviews with these doctors, they all had the same reaction when I first showed it to them. They all said it was wrong. So I'm like, okay, well, have you ever seen a tree diagram or representation like this before? No, but it's wrong. Doctors are wonderful people, but they have very strong opinions, I've learned over the years. So with the first doctor who was getting very frustrated, I said, well, if you say this is wrong, draw me the correct version. And it was, I had a napkin and a pencil at the cafe where we were meeting, and I slid it over to him, and he sketched what he thought the correct 2D representation would be. I was prepared for my other interviews and had pencil and paper, and every single doctor drew the exact same new version on the right. They all did it. Anyone want to point out, there's two sort of major differences between the left and the right. Anyone want to point out what's different about the right? Yeah. Yeah, so the projection's different, right? So I'm in the version on the right, what we're doing is, instead of having this naive sort of 2D square cylindrical projection, it's what I call sort of a butterfly or a pseudo-cylindrical projection. And this is trying to show the narrowing of the artery, because a lot of these plaque deposits squish the artery in, and that helps them look to identify that. And this is called, for them, butterflying. So it's the equivalent of trying to take a artery, and if they had a scalpel, cutting the artery and flattening it out flat. That's what they were going for. So that was the first big change, and they liked that. The second big difference is the layout algorithm I used to order the arteries. On the left, I just had an algorithm to sort of fill up the white space. And the doctor's like, no. I didn't go med school. There's a whole taxonomy and ontology to how these arteries are thought of and represented. So for them, you always have the LAD, which is the longest, like big one that wraps all the way around, and then you sort of have all the daughter branches. It's a hierarchical structure, and they want it represented in a particular hierarchical way, also based on sort of the size of the arteries. So once I got that straightened up, then the doctors were much more, they're like, oh, okay, I got this, I can understand this. And it worked from there. Now, before I talk about color, I always get a question at the end of my talks that say, why did you do a 2D projection like this? There are a lot of algorithms in medical imaging to sort of take the whole artery thing and try and flatten it out, or do like a cut down the middle. There's all these other techniques. I said, well, I really thought for this case it was going to be easier, and I wanted to do a tree diagram representation, sort of take each artery apart. I was inspired to do this type of tree diagram representation from my work I was doing at the same time in astrophysics, where we were using these tree diagrams to represent the sort of hierarchical gravitational structure of star-forming regions. We were inspired in that project by the bioinformatics community that, as you probably all have seen, use dendrograms to help understand sort of gene sequencing and other structural data. That domain was inspired by the evolutionary biologists and looking at phylogenetic tree diagrams to understand the evolution of species. The first of which was drawn by Sir Charles Darwin, and here's a scan from his Origin of Species looking at the evolution of finches. And he was inspired by the linguistics community that used the metaphor of a tree growing to understand the evolution of languages. And they were sort of the first community to do this type of evolutionary and hierarchical structure. So from linguistics through biology and biophysics and astrophysics back to medical imaging. Interdisciplinary. Now, color. Color, I would have to argue, is one of the most important things when you make a visualization. It doesn't have to be imaging like this. I mean, you make a scatter plot or a bar chart. What colors you pick for your data will dramatically alter and affect how people see the data. It will change how their attention is grabbed to or gravitated to certain points in your scatter plot, or if you do like a matrix heat map, what color scheme you pick will change how people highlight and find the most salient parts of your data set, as well as seeing structure and patterns. And this is, again, heat maps. This is really important for matrix. And here I'm doing it with images, where I had the arteries, and I picked 8 different color scales and color maps to go with this image. And I sort of picked the conventional, some not conventional. And remember that for the values of the shear stress, basically stuff below 3, roughly below 3, is considered diseased. So take a peek at these images and pretend you're a doctor and you're trying to find the stuff that, the parts of the artery where there could be plaque below roughly 3 on these scales. Take a second. Figure out which one you like the best. So, anyone want to hazard a guess which one they thought the doctors liked the best? Like the best, or which one you think is the best? They may not be the same thing.
Red one?
The red one being this red one. Okay. It was not their first choice or favorite, but it was their second choice favorite. And I'll get to exactly why they liked that. They liked it, but it wasn't their favorite one. Any other guesses?
I thought the doctors would like the top left one.
That's the rainbow? It's not your favorite, but that is exactly what they like. That was their favorite because it was preferred. It's standard. It's sort of the default in all the existing software. MATLAB used to have as a default Excel. A lot of the software is moving away from it, but for them, that's the default. That's what they're used to. And honestly, a big reason they like it is it's pretty. That's what they said. They said it's aesthetically pleasing. They like the rainbow colors. It's really fun to look at. So that was preferred. It is arguably the worst choice color map from all of these. And anyone who knows me in the visualization community, I'm the anti-rainbow color map person from this research and others I've done since. And part of the challenge is, if you look at, that's the only colored map that has no brightness variation. All 7 other maps have some level of dark to light gradient. And we have more rods and cones in our eyes, and we are really, really, really good in our visual system at detecting the difference between something that's light or dark. But we're not very good at detecting color differences. So all these other ones have like a nice brightness gradient in them. The rainbow doesn't, which makes it much harder to understand. One of the other big reasons the rainbow color map is not good is we are really, really bad at detecting the difference between yellow and green and pale blue. That's like if you look at a spectrum of how we see our vision, we have very, very low resolution and color space around the yellow, green to light blue, which of course is exactly where all the interesting data is in this plot and similar ones. So I sort of said to the doctors, this was well, what other color maps do you like? And this gets into the red one was the sort of non-rainbow favorite. Why do they like it? They liked it because, if they stared at it long enough, they realized there's this brightness gradient and you could really see more patterning and texture in the data. Also, the red has this lovely pop-out effect. We have stop signs are red lights are red, warning labels are red, because we are the most sensitive to red of all colors. And it pops out of us really strongly, and we remember it really well. So they're like, oh, that's nice. Everything that's red is some kind of level of disease. So that worked well for them. They also honestly loved it because of the metaphor of blood being red. It made sense to them at a glance. My hypothesis for what you needed, what was the best, was the top right. I was like, why do we even need to have color? Why don't we just make it black and white? And we're really good at sort of detecting light versus dark, so let's just do a black and white color scheme. Oh, no, 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 no. That was their least favorite one. And it's because it was too radiological. So I learned an interesting lesson on this project that if it was black and white, the doctors assumed it was raw data. They assumed it was like those MRI scans I was showing you, that if it's a black and white image, it's raw MRI data or CT data or raw X-ray. But we passed this through tons of analysis in a computer simulation. So it's been post-processed very heavily. And if I make it black and white, I'm lying to the doctors in essence, making them think it's a raw data set. No. So I learned an interesting lesson, and it was published in this paper, of if you're working in the radiology domain, don't do black and white unless it's actually raw data. Okay, so this on the right was sort of the final version of what I came up with as an artery projection that you don't need to interact with it, and it has a well-designed color map. I built this into a prototype tool, and yes, I did leave the rainbow in there so the doctors would be happy and they could compare it to conventional stuff. And you can actually overlay like 2 sets of tree diagrams. This is a simulation of a very diseased patient at sleeping at rest in a stress test. I have an overview and context setup where there's like a little version of the tree diagram in the lower right, and the doctors can click around and scroll through, and they can mouse over to get details on demand, to get precise quantitative values if they need it. But hopefully just the sort of overview and just the static snapshot is good enough. So I deploy this tool, walk away from it for a couple months, and I come back to the research group I was working with at the Brigham, and nobody was using the tool anymore. They were still they had sort of abandoned it, and they were using the conventional 3D representation. And I was sad, and I tried to talk to them and say, why aren't you using this? And it boiled down to the fact that they weren't convinced that this 2D representation was more effective for identifying these low shear stress regions as compared to the 3D. So I went back to the drawing board, so to speak, and I decided, okay, let's do a quantitative study here. Let's evaluate which visualization is better. Can a doctor diagnose more of these disease regions with the 3D or 2D? And then also color was, okay, so 20 years of psychology lab research says the rainbow color map's not good. Maybe in real life it's not that big of a deal. Maybe it's within a margin of error and it's not actually a big effect. So I wanted to evaluate the color maps. So for my study, I recruited 21 Harvard medical students. These were all students who had gone past their second year, so they'd done cardiology rounds, all their basic training, but they importantly had not been trained yet on the expert tools. So they're sort of like a knowledgeable user base, but they weren't biased by conventional visualizations and diagnostics. And I did a mixed within subject between subject design. So what that means is within factor, every single person who participated in the study saw a series of 3D and 2D visualizations of real patient data sets, and they had to go through and click and mark and identify where they thought all the plaque deposits were. And then between subjects, everyone was either seeing the rainbow color map or the red divergent color map, but they never saw both of them as part of their study, so they could learn one color map and stick to it. In the study, I was measuring, what fraction of the disease regions were found, how many false positives were there, and also how long it took them to complete the diagnosis. And time was important. So time, obviously, in a medical situation is important. If someone's life is in danger, you want to diagnose them quickly and get them into the operating room. Honestly, it's also a thing of money. A hospital is going to be more efficient and make a profit and just be more efficient, getting more patients diagnosed and through their system faster if you can diagnose them quickly. So time was really important. So here is an equivalent, the same artery represented in 3D and 2D, and every single person in the user study correctly identified this red disease region here as, aha, this is a really big, bad diseased region. What did they mess up on? So I'm going to rotate the 3D artery, and there's this little bit of plaque in the bend in the artery right there. And turns out from the fluid dynamics, you get more plaque deposits in bends and curves in arteries. No one got that in 3D. Every single person correctly identified it in 2D. Same with this plaque deposit here and this one over here. So it gives you a hint as to what the results might start to look like. So what were the results of the study? So in terms of accuracy, there was a strong effect of dimension on accuracy. So on average, to look at how many of these diseased regions were found with the low shear stress, on average, participants found 39% of them in 3D and 62% of them in 2D. So I'm still not thrilled with the 62, but there was a significant difference there. I forgot to mention the ground truth answer key for this experiment. I got 3 as lucky. I got 3 cardiologists and locked them in a room for like 2 hours to go through all these data sets. I was terrified. They probably put way more time and attention into diagnosing these than they would a real patient. That's okay. It's fine, but they went through and I had them do it in 3D and then in 2D and double check in both color schemes so that I had this whole ground truth data set to go off of. And then the users say we got 39% on the 3D, 62% on the 2D. But we also studied color. And simply by changing the color map in the 2D version, the average accuracy for the diagnostics went up to 91%. And so that confirmed all the psychology literature that yes, there is an effect of having a brightness variation and using pop-out effects and picking an appropriate color scheme. Now I give you this whole spiel about efficiency. So what did I find for time? So participants were more efficient in 2D. The rate was 5.5 seconds to sort of go through and identify each region on the 3D and 2.5 seconds in 2D. Now what happens if we change the color? Absolutely nothing. There was no effect on efficiency in color. What was happening was they were basically reading across the image. It worked really well in the 2D because they'd read left to right and top down. And what was happening with the efficiency is they kept the same rate going, but they were missing them. So the accuracy was dropping down tremendously. In 3D, it almost doubled how long it took someone to find these disease regions if you switched to the rainbow color map. So the rainbow color map has a greater effect on efficiency in 3D. Now the last piece of this experiment, which was not explicitly designed to be this way, but it happened really well, is a measure of complexity. So it turns out, for your heart, you have a left and a right branch on your coronary arteries, and everyone's a little different, everyone's different, but either the left or the right has more branches and supplies more blood. So you basically have a dominant and a subdominant branch system on each side of the heart. So here's an example of one patient where they had sort of one side, actually I think it was the right side, where they had more branches on one side of their heart and less on the other. And I use this as a measure of complexity. Say, what happens to things like accuracy if someone has just a very simple artery branch system to diagnose and look at versus a larger one? Well, not surprisingly, participants were less accurate in the 3D case with more of these branches that decreased, and people basically were getting lost, they were searching, it just didn't work well. But this was not true in 2D. And in 2D, there was no effect on accuracy or efficiency. So you can make this more and more complex, have more and more branches, and it wouldn't negatively affect the rates of diagnostic accuracy, which was surprising. So in summary, even for 3D spatial data, a 2D representation is more accurate for spatial tasks and more efficient for spatial tasks. And the rainbow color map, while it's not accurate and it's not efficient, has adverse effects even greater in 3D. So really, really, really don't use this. So if you take away anything from my talk other than put titles on your graphs and label your axes and annotate your plots, is if you have scalar data, please don't use the rainbow color map. And then a few final remarks on this is that the 3D representation is still essential for surgical planning. The comment here is not, avoid 3, it's pick it appropriately. And a lot of my current work, as I'll mention in a second, relates to this. So you still need that 3D representation for doing the surgical planning, bypass surgery, stent insertion planning. And the 2D tree diagram is applicable to other applications, things in, medical like pulmonary airflow, other blood flow, and I've also used it for other sort of fluid dynamics and engineering and blood flow cases. My current work, what I'm working on right now with my students, is a lot of follow-up work to this, and we're doing stroke diagnostics, and here's some of our prototype work. And again, it's sort of boiling down to having a 2D representation that makes it really, really easy to find blood flow anomalies, but it's different. The physics of it are different. It's sitting in your head, so it's all squishy and floating around. It's not in hard muscle. There's all these differences, so we're working on expanding this into the brain. Now, Dan, let me ask, what time do I go till again?
It's 9:55.
How much more time do I have? 10:30? Oh, good. I have lots of time. Good. Now you get to hear about astronomy again. And I'll have plenty of time for questions at the end. Okay, so I just talked to you about cardiology. And we have a situation where we have the doctors have their conventional 3D, and it's also really important for doing surgical planning. They also have the raw 2D data, and the doctors a lot of time really want to see this raw 2D data as well and sort of look at the actual data in the anatomy. They have these data abstractions like the tree diagram I have here for looking at diagnostics, and I didn't even get into it today, are like all the other statistical plots of looking at heart function and blood flow rates and looking at thickness blood. So there's all these other statistical plots. And outside the task of I have a patient and I have to diagnose them quickly, if they're sort of taking a step back and doing a sort of reflection on the patient, a larger dive into the data, trying to look at everything, or if there's a medical researcher who's doing research on this, they need to have all of these together. And then guess what? The astrophysicists need the same exact thing. They have the 3D representations. This is the L1448 star forming region, and the raw 2D data from the telescope, and the abstraction to look at, in this case, the gravitational collapse inside the cloud, and statistical plots. And in this case, they're even looking at properties to compare this to computational models and simulations of the star forming regions. And this sort of holistic 3D, 2D, and all these other plots is common in the imaging sciences. It's common probably most everywhere for data visualization, but particularly in the imaging sciences, this is quite ubiquitous and really common. And what someone wants to be able to do, be it the doctor or the scientist, is they want to be able to select, as I've highlighted here in red, voxels like in the 3D, like build a cube, and then or mark parts on an image or select bars in a bar chart and have it linked in red. If you interact with one part of this visualization, any of these, it's going to identify the equivalent data for you in another plot. And this is vital for doing data exploration and data analytics. In order to do this linking, and the term in HCI is brushing and linking because we have to brush and paint over the data, is you have a gluing problem. You need to do data management on the back end. You have to say, if I select data in this 3D volume, I want it to highlight the appropriate data points in all these other plots. If any, raise your hand if you've used Tableau. I'm really curious. Okay, a couple. So Tableau is my best example for doing really good brushing and linking, and you can select points in a map or rows in a table, and it's going to highlight them in all of your other visualizations. But the problem is something like Tableau only works on tabular data. And in fact, generally it's one Excel table, it's one giant table, and then as you select columns or rows, it knows how to do it. This gets really impossibly challenging in the imaging sciences, where you might have different variables in different values in each one of these. So the astronomers might have the image, the XY and the XYZ for a 3D rendering or a 2D, but then they have statistical plots and data abstractions that may not have all the same variables and all the same spatial dimensions, and how you map and do the linking. So this is, and the doctors need this too, and this has sort of been this barrier to get across, is how you do effective interaction as well as effective data management on the back end. This was a goal of mine and Alyssa Goodman, who's an astronomer over at Harvard for years. And after years of development, we finally have built a user base and put together a tool that I'm demoing in this video here called GLUE. And you can see a gigapixel image of a star forming region, and we can brush and link and select points in the scatter plot, and it's going to update our selection in all the other plots, and we can drag and drop variables and data sets across and do things where we don't have to load the whole image from memory. We can do different parts of this, and this is all in a tool called GLUE, and it's freely available, open source at glueviz.org. For better or worse, this whole workshop is beautifully done around R, and I'm a huge fan of R. This tool is all Python and links to, especially in astrophysics and medical imaging and the chemistry communities I've worked with, a lot of their toolkits are in Python. So that was part of the goal there, was to make this open source GUI-based tool, and it can sort of read in and connect with other Python applications and code bases. And I have the lovely little JWST logo here. Most of our work is funded by NASA, and we are the official visual analytics toolkit for the James Webb Space Telescope, which will be launched in about almost exactly 2 years from now to replace the Hubble Space Telescope. And okay, so NASA pays for us. Our primary clients are astrophysicists, but it was built from the ground up to be interdisciplinary. It was actually always built with my collaborators that the underlying architecture would be completely domain agnostic so that we could make it open source and open to other communities as well. And here, I threw this in here. We just had a new version released last week. I was very excited that we now have a whole bunch of spectral line viewers and spectral analysis tools as part of this. So again, JWST is going to have an incredible set of instruments for doing spectra of stars or basically anything in outer space. And here we can do individual or areas where we can identify. This is looking at isotopes of carbon monoxide, in case anyone was curious, looking at 12 and 13 CO. So now we have a lot of these beautiful tools in there for doing spectral analysis, and some GUI tools for doing like very basic fitting and analyses of the spectra. But we also have a plugin you can link through Python to do more sophisticated stuff. And here's a demo working with some more high-res astronomy data. And you can see me brushing on the bar chart and going through, and it updates the selection in the scatter plot and in the image. So this is sort of a very typical astronomy work case, but we also are doing a lot of GIS and geospatial science research now. And in this little demo, I brush on the scatter plot, and we have brushing and linking in 3D, and you can also select data in the 3D. So this is looking at earthquakes around the world, and I selected the core to sort of say, why are the earthquakes happening really, really deep? And there are very few, if any, tools out there that can do this kind of brushing and linking in 3D. And then we're obviously working on medical. So here are two different two data sets for one patient that we superimposed with volume rendering and letting a doctor sort of go through and look at it. And then if GUIs are not your thing, well, you can control everything from the terminal window. So we have an embedded IPython window in the toolkit. So you could basically type there and you can do everything in the GUI by command line plus more. You can do a lot more work, and you can load in your own Python libraries and your own analytics. Kids curious, that data set's taxi rides in New York City. And sort of looking across all of these, are sort of built GLUE to be this very interdisciplinary, broadly applicable solution for the imaging sciences. So that's the end of my formal slide deck, but I made sure to leave enough time to answer questions, and I have a whole bunch of hidden slides and other presentations I'm happy to pull up as well. But I really hope you sort of through this saw at least a couple examples of other domains in the sciences and sort of saw the value of visualization. And now the next couple days, you're going to get to do a deep dive and learn some really great technical and practical skills using R to do your own plots and your own visualization work. And then again, Stephen Braun will really nicely piggyback off of what I've talked about to talk about information visualization principles and perception. So, thanks. So questions can be about anything I show you here, and it can be about anything I did not show you, and I can talk more broadly. Yes?
Hi, so going back to your angiograms, why don't you just design a computer algorithm that can pick up the changes in the blood flow, or identify the areas that are low ESS?
Yep. That is a fantastic question. Let me find a good slide just so I can have that. Let me pull up. Let me just go up to here. Okay, so the question is that if you look at this, a lot of this was visual exploration, visual exploratory tools. But why can't I just have an algorithm that thresholds it or identifies the regions of low shear stress? So on the first pass, just simply thresholding, because that's something I get where I can just pick a shear stress value and just mask everything above and say, okay, I'm only going to show the diseased regions. Part of that is basically the doctors don't agree on what is diseased or not diseased. Like there's these vague ranges, but there's a lot of ambiguity, and different doctors have different interpretations, and different patients exhibit different blood flow patterns. So when I was doing all my interviews and development, the doctors didn't, I want to, and I'm actually my stroke work, going to give an option so that a particular doctor can just threshold themselves on the fly, but I didn't make it part of this tool because I wanted to leave it open and flexible. Also, the doctors care about patterning at the high shear stress realm. It shows them not heart, not plaque deposits, but other blood flow anomalies. The more interesting question, which I think you were also alluding to, is I could do like a machine learning algorithm that goes through and identifies or gets trained on a bunch of data sets from these doctors. My biggest hurdle there is actually, it's not technical, it's a cultural problem. And it's a cultural barrier of the doctors not wanting to deal with, they don't want the computer to tell them what's a disease region and what's not. So on the cardiology work I showed you, I sort of walked away from that. On my other work with brain tumor and stroke and glaucoma even, I'm trying to tackle that where I have a visual exploratory tool. So the doctor's in the driver's seat and they can do what they want to do, but I'm right now evaluating different ways of having, for instance, after the doctor diagnoses the patient, the computer can nicely say, are you sure you're done diagnosing? You might have missed something over here, and very politely point out to the doctors where our algorithm has found some interesting things. And our algorithms, even the best ones we're coming up with, can't get above about an 80% accuracy anyway, so I certainly like having the doctor in the driver's seat, but the case is a visual attention problem. If the doctor's looking over here and they just miss some obvious thing, you really don't want them to miss some obvious thing. So I'm right now working on this sort of explainable AI problem to it's not explainable AI, it's more like AI integration, to have something in the background and then the doctors have a way to have it suggested to them or highlighted to them to sort of identify it. But I'm actually working on that right now. And then the shear stress problem for the cardiology very specifically, there are some groups working on machine learning algorithms and similar algorithms to identify and find the shear stress, but it's quite challenging. It's not as straightforward as one would guess, but it's coming. It's there. But it's a really good question.
Right. So it's challenging because there's no correct answer.
Yeah, and a lot, yeah.
It really becomes an issue then, because so what you said before, as far as having 3 cardiologists in a room for 2 hours, and if that's the truth, what I'm hearing is that may not be the truth.
Well, I should say it's challenging, meaning the doctors pretty much agreed on what's diseased and what's not diseased, and the algorithms, for the most part, they can get the big stuff. It's the subtle, weird, unusual little things that is where I have a friend down at Duke who's working on this, and again, it's mostly there, but it's also the algorithm trying to find the exact patterning. I can pull up all the detailed papers later. I say it's basically what I'm trying to say is the work here is correct. What the doctors marked was correct. Moving it to an algorithm works well for the big stuff, but gets challenging with the little weird detailed stuff. Yeah, but it's fascinating work.
Sure.
Yeah.
One more question I have is, in that particular study where you had 39% versus 62% for these medical students, how do you think the results would have changed if you tested a group of people who actually knew what they were looking at?
I don't have it as published work. I have done this unofficially with the same group and had them go through. Overall, their accuracy levels are higher. That it's like you take those values that even with the rainbow one, they probably can find a little more, but the sort of range and the overall trend is the same. The trend's the same, even if the really officially trained doctors can do better. And even if they're like, oh, I don't want to look at the 2D thing, they're really good with the 2D projection.
And it's still significant.
Yeah. Yeah. And when I'm working on the stroke work right now, I'm going to try and do that exact study. That's my hope, to do the 2 user bases. Other questions about the particular projects I showed you or other visualization in general? Yeah?
You obviously do a lot of collaboration across a lot of different disciplines that probably come through challenges in communication. So, what kind of language do you find yourself using and maybe altering the way that you're talking about your work in order to communicate effectively with people from different backgrounds?
Yeah, so that's why I love my job, and that's the hardest part of my job. Is sort of the question is how I do this interdisciplinary collaboration and work with all these different domains and all these different scientists. And what I've found is there's definitely a lot of diplomacy involved. There's a lot of sort of working on good communication skills. Honestly, the biggest part of it though is finding good collaborators. That's the secret sauce. So I've tried and had tons of projects not get off the ground because even with my best communication skills and my best let's talk, here are these interesting problems, it never gets launched, mostly because of bad collaboration and bad team dynamics or people not all being invested or having the same goals. And it's more of a social thing than anything else, or collaborators who initially say, yes, I want something new and better for visualization for my work, but then as you start to build, you realize they are quite set in their ways and they don't want to see anything differently. And it's like, from a research, engineering could be one thing, but from a research point of view, you have to walk away. So so my biggest challenge with doing these broad interdisciplinary applications and research agendas is finding the good collaborators and finding those who are really engaged and enthusiastic. And even if we are speaking different languages domain-wise, if everyone's sort of vested in it, then you can take the time to perfect the communication skills and get it across. I think the other sort of special part of doing these interdisciplinary collaborations is making sure your team has people who can speak different languages. So I've gravitated towards doing projects in the physical sciences mostly because that's my background and I can speak math, I can speak stats, I can speak physics. Over my dissertation, I learned how to speak radiology, if you will, and I've spent years now at the medical school. As part of my dissertation work, I ended up taking a whole bunch of biophysics and bioinformatics classes so I could learn how to speak those languages and do more biological related work. And there's cases where I did a wonderful project recently, or a couple of these with psychologists, and the key to the success there was finding postdocs and grad students to work with me who had that background. So I basically, if I don't have the languages, I find someone else who can help do the translation work for me if I can't do it. But it's a fascinating problem and challenge. One person who recently published a wonderful book is Ben Schneiderman, and it's called the ABCs. I think it's vaguely called the ABCs of Research. And Ben Schneiderman is the guru, amazing, huge figure in the human-computer interaction and visualization research communities. And he recently retired. He's emeritus, which means he's writing tons of good books and giving wonderful lectures around the country. And he was at Northeastern a few weeks ago, and he gave this wonderful talk about the ABCs of research. And the C, I believe, is collaboration. But a large part of his sort of how you do really effective research in general, not just computer science, relates to collaboration. He actually does a beautiful job in his book of sort of talking about strategies for doing interdisciplinary and collaborative research. So you can look that one up. Other questions? Yes?
Actually, I have a question about this.
Sure.
How do you resolve the biases? Let's say you have these arteries of in some regions, they're overlapping with each other.
So you need to differentiate, right, one region from the other. So do you, in this segmentation, so when you come up with the 3D image, 2D image, to the whole outfit,
You're saying, so the way it's working in real life is they don't physically intersect each other, like each artery is its own branch, but there's branching points, I think is what you're referring to, where they sort of stick together. And basically what's happening here is where the line goes is where one piece connects to the other. And it's hard to see, but basically this is wrapping around this part here. And there's a lot of subtleties in the algorithm of how it's pulling apart and stitching it together. And part of it is putting a little redundancy. It's hard to see, but there's some number of pixels of redundancy between the branch that's coming off and the home branch. And the hope is you'd be able to see, if there's a lesion there, if there's a plaque, that if you sort of like, you're going to see it on the main one or the little one, you know, the branching. But that's a really good point. And there's a solution for this project, and it's good enough, but I feel like that's a great area of future work to come up with an even better solution. But for this one, there was no pixel overlap and trying to also pick at the right spot. Yeah. And then it does get really icky and complicated because there are some patients, it's rare, but if they have a blockage, there is a case where they can grow an artery around a blockage. You see this with athletes who have really great circulatory systems. I haven't even started to think through how to deal with that subset of patients because it doesn't really fit this model. Other questions? Yes, in the front.
You talked about getting the 3D model. Tell us some more about how you actually get that.
Sure. So let's see. I have a slide for that. You're talking about this, where...
Yeah, you said they use dye and then...
Yeah. So, yep. So the way this works, let me pull the first few steps of this up. So the way this works with the CT is, right, so it's a 20-minute sequence, and what they do is, and it's a pretty much, it's called CTA, CT angiography, and you go in and they give you, while you're in the CT scanner, they have basically a shot that has a contrast dye, and I'm trying to remember which, I can look it up for you if you care about exactly which contrast agent, but it basically comes out dark on a CT, which is essentially an X-ray, but it comes out dark in the CT scan, and they do the injection, and then they do a series of really fast images over the course of a few heartbeats, and you can see, it's pretty cool, where as the dye propagates, you know, and goes through the heart. And then you can look at that data, and some doctors like to do this, and some of my stroke work, I'm doing this as a time series, so you can see it. But in general, the vast majority of doctors, what they do is they use an algorithm that comes as a post-processing in the software for these scanners that takes each time step as the dye is propagating, and then it sums it up. It basically does a integration, I think that is the correct term, to put all of those time series together, and then you get a whole complete picture as the dye propagates, so you can see like literally where those arteries are. And that's what, so it's the summation is what we're using for doing the segmentation. So we've sort of seen where this fluid flows through, and we sort of have a complete picture of where the arteries are, and then we're segmenting and identifying. And we do this by slice, and then there's a few algorithms for this. One is you can go slice by slice, and the algorithm marks, draws a circle, just like these little pictures of where the artery is. The better, more sophisticated ones we now had working at the end of the project do a 3D watershed, and it actually puts like a little seed point and does like a 3D volume filling through the artery branch structure to try and do a more complete. And that step also, sort of going from segment arteries to generate, this is, I call semi-automated. A human being has to check it. So they have these labs at the hospitals where even if an algorithm, a computer goes through, they have a human being go slice by slice through the MRI or the CT data set to make sure they agree with where those lines are drawn. And if a human being thinks the algorithm made a mistake, they can have these editing tools to redraw it. That's sort of the arrow in between segment and generate, and then it goes into the let's actually make a CAD-related model and make sure it's okay. There's a lot of work too here that goes into how making sure the algorithms work correctly, and that like it's all working. And a lot of it's done with what they call phantom models. It's pretty cool. They do 3D printing now of arteries or of simple tube structures, and they will put it, in there, and then they have like a physical real thing they can measure against different CT scanners and different people editing the data. And there's like this whole, FDA and like really important, NIH approved and IRB protocol to get it working. I could talk a really long time about this. Does that answer your question, or you have other specific? Yeah, in case you're curious, it basically works the same way with MRI. Obviously, the data acquisition is a little different in terms of the physics for MRI, but it's the same thing. Instead of 20 minutes, it's an hour, but it's the same thing. You go in, they do the same injection. It's a different, chemical, and it works the same way. Other questions about this project or others? Yes?
So a more general question
Yeah.
about visualization. In biomedical, we see a lot more things like PCAs and TCAs and new strategies of like producing these high dimensional data sets and distilling some sort of information about that. So if you could just get your comment on those strategies and where they're applicable.
Those strategies are super duper important. Oh my goodness. I teach those sort of in the end of my class, and I want to do like a grad seminar on this, is the importance of what we call sort of data filtering, aggregation, and analysis. That I have I have a project I did with computer scientists looking at file systems. And this is one project near the end of my dissertation, and it was really impactful for me because I tried to just take the raw data and visualize it, and it failed miserably. And that was like my real hands-on experience, and I had to write and do a whole clustering algorithm to get it to work. And I realized that important step that you can visualization can't always be the super perfect thing that's going to do it on its own. That if you have the raw data, that many times there's no way around it. You have to do dimensionality reduction or data aggregation in order to have something that is intelligible and simple and easy, and then you can visualize it. So I'm a huge fan of all things like PCA and use it. And it's domain specific and sort of data specific, but those are really important steps. A lot of times when I work with scientists, what I try and do is they're trying to visualize all of their data at once, or I make them sit down and think, is that the right thing? And should there be an algorithmic step in the middle? So I think you guys are going to do a lot of that work too, which I was thrilled to see that on the agenda. It's really, really, really important. Other questions? Yes, unless there's someone else, go for it.
You mentioned briefly that the time series data, and in this case you were saying it was sort of averaged eventually, but that's also something that concerns a lot of folks here. If you take high-dimensional measurements over short periods of time, how do you make sense of that? And I was wondering, what are the frontiers of the visualization front of helping to make sense of like maybe helping to make sense of time series data at all, but also like high-dimensional time series data.
Thank you for helping give me some good words for my next NSF proposal. So the answer is that is a big thing, and time series and time visualization sort of work is quite popular. There's always a track of it at IEEE Viz. I don't think there's enough being done to work with scientists, with real data, with really interesting time series problems, especially with high dimensional. So I have a PhD student, Misha Swab, and we've been working, his dissertation is now going in the direction of doing time series data and timelines and how do you interact with that. And my glue project I was talking about, we're actually working on and brainstorming how to get time in there for exactly this. If you're a scientist and you have data that's acquired in some time series and you want to either just control how you see the time series, or you have time series data of some kind and you want to be able to analyze it and then do sort of sophisticated exploration, we're thinking about that. NASA cares about that. It's on the to-do list. But there isn't a huge amount out there out of the box. There's essentially, if anyone knows of good GUI tools that do this, tell me. I think there's a lot that's super duper domain specific or instrument specific to try and do this. but there is no larger solution. There's obviously a whole body of work on time series analysis from the statistics point of view, and there's time series visualization, but sort of marrying these as well as having real domain applications is sort of a work in progress. I'm trying to think if there was something else I was going to say in that regard, but now I can't remember. Yeah, but time series is really important. Yep.
A follow-up question on highly multidimensional data. Because what's your opinion on how to deal with dimensional data where your resolution is different per dimension?
That's a lot of what we deal with in Glue. That's a lot of what we're struggling with and trying to figure out right now. And it's hard, is the short answer. It's hard. My general thinking on dealing with high dimensional data, it depends on your data, but you have to think of creative ways to, if you want to look at it. Or I have cases where you'll have, some of my simulation data is high dimensional, like one data set, but a bazillion variables. Other high dimensional is like the astronomy, all those 3D visualizations I'm making are these spectral line data cubes, and that visualization is only like a piece of it. So one thing is, honestly, what I call is small multiples. That's my first very generic suggestion, is doing lots of little plots. 3D gets tricky because of perceptual issues and occlusion issues. I have done 3D scatter plots for certain things or 3D surfaces, but you have to do them very, very carefully because it's hard to analyze them. So then it kind of boils down to going one step back upriver and looking at your analysis. Dealing with different resolutions is fascinating and challenging, and I don't have a good answer for you off the top of my head, other than I'm thinking about that right now with a lot of the astrophysics data. So you can, if you have, I think we'll have time. I'm gonna stick around the coffee break. You can always show me what you have, and I can look at it. But it's hard. I know that wasn't the answer you were going for. Any other questions before we break for coffee? Yes.
Do you have general advice for moving from a concrete spatial visualization, visualizing data as it is,
Yes.
to an abstract visualization that, the example you showed, can be more effective, but it also kind of adds a cognitive load on the viewers, especially if they haven't produced the image, so you have general advice.
Yeah, no, well, going 2D helps, especially like in the case I showed you with certain tasks, like clearly with specific tasks, it's going to help you, especially with spatial. But there's two big problems. One is it is a cognitive load, and that's something I didn't measure in the study by measuring, and my current ones are actual measures of cognitive load and understanding what's the barrier to learning and looking at an unfamiliar visualization. The others, I'm throwing dimensions out. I'm throwing data out when I make it 2D. And I think that's one of those interesting steps. If you have 3D and you feel that you need to make it 2D, it's picking the best. You have to compromise, and you have to know very clearly what is the most important data to show, what information can I not throw out, and what things can I throw out. We do this all the time with maps. That's like the whole realm of cartography, because the world is a 3D globe, and we look at maps, even on our phone, and every time you make a 2D map, what projection you pick and what layers you plot on your map is an important step. You're throwing tons of data out, and it's a nice parallel to sort of think about that. And do you use a Mercator projection or a Gauss-Peter projection? And does it matter where you are in the globe and what layers? So it's a really interesting, broadly applicable problem of going from 3D spatial to something flat and figuring it out. So my general advice is, really task and domain specific. That just you have to know what is the point, like what is someone trying to get out of the visualization, and if you make it 2D, presumably to improve task efficiency, you have to make sure the data you're throwing out is not important, and that you're making compromises, and that it's not too taxing on the cognitive load. I think anything, if you go 3D globe to 2D map, that is a higher cognitive load in many ways, especially if you look at the polls, to think about what you're looking at, but it's probably worth it. That's a really good question. Okay, other questions? Yes?
So I was just curious, since we'll be, so like in this course, we'll be working with a lot of making plots from code and that sort of thing.
Yes.
And lots of times when you do sort of this sort of visualization, give it to someone it's all really gooey. I was wondering if you had any thoughts on how languages create graphics and how important that might be in like having in like programming languages that might take different approaches to creating plots.
Yeah, and it's interesting, and it gets back to, it's like the 3D projection. It's what's your task and what are you trying to do? So a lot of different languages vary. For instance, R is, and using ggplot2 is brilliant, and I advocate that for anyone who's clearly using statistics as like their driving goal. And you can't, obviously there's other stuff, but R dominates it when you have statistics and analytics. And it's like, well, you use that visualization language to fit your workflow and fit the pipeline. If you're doing the 3D stuff, then that's a total different set of languages of ITK and VTK and some other 3D libraries. And then you also have the Python. So for me, a lot of the languages is less, in general, is more about domain specificity, and pick the language to do the visualization to match like what's your overall goal and domain. But then there's like some subtleties to how so for instance, I teach in my grad level and undergrad classes D3, which is the dominant web-based visualization toolkit, which I will even go on the record on saying I'm not a fan of, but it's the best out there. And it's just because web-based programming is just, it's all JavaScript, and D3 is sort of the most robust thing. I have a bunch of competing colleagues who are pushing for something called P5, which is derived from processing, which I learned. It was fantastic as a language. It was a Java-based one. That's what I learned as a student. And P5, and it's an interesting programming language question, is fundamentally built around the task of learning the basic visual primitives of a visualization. So it's super easy to code in, because what you're coding are, here are axes, here are dots on my plot. You think very graphically, and it was built by people at the Media Lab, so it's very focused on art and design. So building code in P5, even though that's a wrapper for JavaScript, is very straightforward, but isn't as robust. Like, you can't do as much, and you can't do as much customization necessarily, versus something like D3, which is a heck of a lot harder to learn, and the linguistics of the programming language are not conducive, or it's built for visualization, but it's still hard to do. But it's far more robust. You can do more interactive stuff. Like, there's all these other advantages, but you have to think about how you make your plot totally differently. So it's something I struggle with, and I'm still struggling with when I teach visualization, like past GUI tools. Like, do you pick the thing that's going to help the CV and domain relevant and robust and interactive, or something that makes intuitive graphical sense? And for the record, I think ggplot2 is really great. It's built off of Grammar of Graphics, which is a canonical work by Borkin in the visualization community. So that's one of those languages that is a little more intuitive to think about how you're graphically doing it. But now in that little picture of visualization and coming from stats and computer graphics, it kind of gets in that computer graphics and computer language thing. Does that kind of answer your question a little bit? And for anyone who asks me, like, what do I code in? Oh my goodness, my students and I work across multiple things. We do web-based things, we have Python GUI things, and Java-based GUI things, and it's sort of all over the map. MATLAB, we do a lot of MATLAB stuff too. And a lot of it's just what's the domain and what's the task. Yeah, and then the education's like a whole nother question. Any other questions? Again, I'm going to hang around here for a while and hang out the coffee break if anyone wants to come chat with me further. I think we're all set. Thanks.